Okay, so today we'll see what computational design and analysis we can be done on stents. Stents, as we know, are the mechanical component which are inserted into coronary arteries to prevent the plaque collapsing the stents. So this is typically a one cell mirrored component. So this is typically a one cell component. So this one is a one cell and this is mirrored into this, so it forms 1/24th part of the whole stent. So it is an axisymmetric model and it has been ray traced here now, so you can see it very clearly that you can see it's like a real looking stent kind of structure. So the whole stent would be around, the axis would be passing through it, and we'll see like how whole stent we can look. So see here, this is an axisymmetric model of a stent, and you can see that the plane, this one and this plane, passes to the center, and this is the center line. Okay, so now in this video we'll demonstrate how we can do an FE analysis on it, and validation will be performed in subsequent videos. Okay, so let us see what can be done in this on stents. So what I'll do is I'll like export this model into ANSYS, and we'll make use of ANSYS transient analysis to do an FE analysis on it. What we'll be doing it, let us see. So I have already opened an ANSYS module. So this is transient structural, and now I'll be going into model. So I have already performed an analysis and I have done all these things. So we'll go into geometry or we'll directly go into the model. So let us see. Okay, so here this is a transient structural model and this is geometry, which has been this. There are two coordinate systems, like there are many coordinate systems. So this one is a global coordinate system, like this one. Now this one is a cylindrical coordinate system, as you can see, the cylindrical coordinate system, and this is plane 4 and plane 5 symmetrical planes which have been defined into geometric module of this transient structural, and this is an XY plane. Okay, now you can see there are symmetric region defines. So the major point here is to understand that why these symmetric planes have been defined. So this is defined because it is symmetric around the circumference. If you can see from this coordinate system that if we go around the circumference, this model is symmetric. So beyond this plane and beyond this plane, the model is like the same only. So that's why we have given the symmetric boundary conditions on it. So the symmetric boundary conditions are given symmetric region 1 and symmetric region 2. Okay, you can see the mesh. It is not very fine mesh, but for this system laptop capability, it is quite good, quite enough mesh. There are around 1 lakh nodes, and so there would be around some 3 lakhs equation to solve. So it is quite sufficient and we can get results within very fine time. Okay, we can observe that there is amount of skewness in this which has to be improved. So there has to be some more work has to be done on mesh, but rather this time our focus is on finding some stresses and deformations while applying the pressure and applying the boundary conditions. So we have seen that there is an axisymmetric model, and which means that when the stent will apply some kind of pressures in the inner wall or outer wall, it should expand in proportion to it. So analysis settings can be done on it, and there is only one step. So cylindrical support has been given, and the major thing we have to define is cylindrical support is radial it is free and axial and tangential it is fixed. Okay, so there is no movement in axial as well as tangential direction. There is only a movement in its kind of the radial direction. So radial direction is this one, so it will move only in this direction. We'll see further. So what we have given is we have given the displacement to this upper boundary, and the displacement given is around 1 mm, and 1 mm in direction where in negative direction. So it should compress. Okay, so there would be around some tensile stresses on this boundary and compressive stresses here. So let us see. The solution is already there. So there's an equivalent stress. You can see the equivalent stress, and most part of it is on the outer surface. Okay, you can see it very clearly that the most part of it is on the outer surface, and the stresses which you can observe from the full body is around this one, so which is bearable, and we can manage with this stress. There is no problem in this stress because some yeah, we can manage with this stress. But this one, this stress is too high, and we need to look out, or because this is compressed 1 mm. So I think this is structural steel, and structural steel cannot be compressed 1 mm because this is beyond ultimate tensile strength or ultimate yield strength. So this will fail here at these portions, so the permanent yielding will take place, and so we need to look out. But this is general FE analysis on how it will respond in particular pressures or displacements. Okay, so let us see how it simulates. So you can very much clearly see that how it is compressing, and due to an axisymmetric boundary condition, it is compressing like this. Okay, so it is very much clear that how it is compressing. You can see the directional deformations also, and these are the directional deformations, and you can see that directional deformations around 1 mm because we have given 1 mm, so there would be around some 1 mm deformation, and this is minimum. Okay, so okay, we would also like to find radial stress. So what we'll be doing is insert stress, and it would be normal stress. So normal stress, or what we'll do is we'll delete this one, and we'll go into user defined results, and we'll go into user defined results. We'll select the coordinate system, that is a cylindrical coordinate system, and we'll give as SX. Okay, so it should give me the radial stress, and let us see what it gives the radial stress. So you can very much clearly see that throughout the thickness the radial stress is somewhat constant, and it only appears on this. Okay, so it is very much clear that because it is kind of thin cylinder kind of geometry with spaces in these parts, so it is spaces in these parts, so this one is like there is a constant stresses in the radial direction along the stent. And the other variation what we can do is we can remove the displacement here, and yes, we can remove the displacement, and what we will do is we will insert the pressure. Okay, so you will apply a pressure, geometry selection, let us do geometry selection, apply pressure, and the pressure has to be applied in 9 power. So we have applied 1 megapascal of pressures, and let us see how it solves. You can go into solution information and then see if whether the solution is converging or not, and let us see. So it would take around some quite amount of time. So the first iteration results are there. I think it will be converging because in the first iteration only we have force convergence value somewhat close to the criteria what is used to this, and let us see what happens in subsequent iterations for force convergence as well as displacement convergence. Both of them should converge for solution to, so that we can get proper solutions. And this would be a kind of iterative solver. There is also another kind of direct solver. So you can see that force convergence is reaching near the criterion, and you can also see that displacement convergence is also reaching the criterion. Because of proper symmetric conditions and boundary conditions, there is no problem for it to reach the convergence value within few iterations. Okay, so in second iteration only it has reached the convergence value. Okay, force. So I think in this iteration only displacement convergence will be reached, So let us see. Yeah, so both of them, like force convergence as well as displacement convergence, has been reached and now solution is over. So let us see what happens. We will see for the equivalent stress. You can see the equivalent stress, and you can see the directional deformation. The directional deformation is too low in direction of x-axis for the coordinate system, this one, and we can see that directional deformation around is very much like it's around micrometer. Okay, it's around micrometers, and we can assume that when we, so it's quite natural that in previous result when we have given a displacement around 1 mm, so it was huge stresses. So now they are not huge stresses, and it is quite around some yield strength of structural steel. So we can have user defined results, and we observe that they are in in synchronization with what we have expected. So we'll run the simulation and let us see what happens. So in true scale we cannot observe any kind of displacement because it is too small displacement. So if we do it as auto scale this, so we should be able to see some kind of destructured kind of thing. So we'll go into this one, and I think we should be able to see some kind of displacement here. See, you can see some kind of displacement here. So the further modification which can be done on this kind of structures is we have only included this bridge. So there can be several bridges, and then I think the stiffness of the structure will also improve, and radial strength, that is radial stiffness, can also be improved. So that kind of analysis has not been done till we have not done the kind of analysis for radial strength, but it is very easy, and the validation for these results has been in progress, and shortly I think we'll be able to do the FEA validation. So thank you for watching the video.